Now let us describe the relation between different dielectric parameters. Before going into details, let us first define some important parameters, new parameters regarding the dielectric material. First one, number one, capital D vector. What is D vector? This is called electric displacement vector. It is defined as the electric flux density, that is the number of lines of forces crossing normally per unit area of the surface. If Q be the total charge of the surface and A be the total area of the surface, then Q by A is the numerically equal to the electric displacement vector. It is a vector quantity, that's why this is called electric displacement vector. In short, it is defined as D vector equals to epsilon into E vector. This is the relation between the D vector and the electric field vector. Epsilon is the permittivity of the medium, so epsilon can be written as epsilon naught into epsilon r, free space permittivity into relative permittivity or dielectric constant times E vector. Now let us find out the relation between the D vector, E vector and P vector, electric displacement vector, electric field vector and polarization vector. In order to describe the relation between these two vectors, let us start with the relation between the external electric field and the polarized field. We have already described earlier about the internal field or induced field and the external field. So suppose this is the dielectric slab which is placed inside electric field, external electric field E naught, and this is positive, this is negative side of the plates. So inside the dielectric, this side is positively charged, this side is negatively charged. So inside the dielectric, the induced or polarized electric field EP just opposite to E naught. So as a result of this, E equals to E naught minus EP. It is already established earlier. Now here, this electric field E naught can be expressed as sigma by epsilon naught from Coulomb's theorem. Sigma is the surface density of charge of the plate. Epsilon naught is a free space permittivity, since this space is filled in air or free space, and EP can also be expressed as sigma p by epsilon naught, where sigma p is the polarized charge density inside the dielectric and epsilon naught is the free space permittivity. Here it is our assumption that within the dielectric the permittivity is epsilon naught. So putting this value in this expression, we have E equals to sigma by epsilon naught minus sigma p by epsilon naught. So epsilon naught E equals to sigma minus sigma p, or sigma equals to epsilon naught E. Sorry, these are the vector quantity, the scalar quantity. Anyway, in terms of scalar. So this is the expression. So sigma equals to epsilon naught E plus sigma P. Now sigma P is the polarized charge density. So this indicates the polarized charge divided by area, polarized charge density. So we may write, if a T with the thickness of the slab, we can multiply and dividing by T. So this indicates net dipole moment by volume. So it is nothing but polarization vector. So sigma P is numerically equal to, in terms of scalar, numerically equals to polarization vector. So putting this value in this expression, so putting the value of sigma P in this expression, we have sigma equals to epsilon naught E plus P. Sigma is nothing but D vector. It is already established earlier. So D vector equals to epsilon naught E plus P vector. So this is the required relation between D vector, E vector and P vector. In absence of polarization vector, D equals to only epsilon naught E. If P is 0, D equals to epsilon naught E. If polarization is present, so D equals to epsilon naught E plus P. So this is the required relation between D, E and P vector.